This is the presentation from Mobile World Congress, Barcelona 2025. Specifically, we're targeting AI defect inspection at the edge using this technique we call specular metrology. We're going to go through 4 sections. Essentially, what's the challenge? How do we automate this process of inspection? We're going to look at some use cases, and then we're going to look at the types of materials and defects that can be detected. So this is a big challenge. There are 35 million estimated visual inspectors around the world. So when you think about manufacturing, there's a lot of people sitting there, particularly where you have things that are shiny and transparent, where it's very difficult to automate and you have people in the loop to try and find defects, but also to put a little sticker on those defects so those may be dealt with later. So whether it be an iPhone or a car or the fuselage of an inexpensive plane, for example. Now, there are automated technologies which use things like X-ray. Certainly, visual inspection is very possible where surfaces are more diffuse or matte. But there's a whole category that fit into this shiny and transparent section. One of the other challenges is latency. So if you're trying to transmit this data back to a cloud, to your AI factory to do the processing, that's a lot of data to send, particularly if you're manufacturing a lot of something. So part of this solution, we're going to talk about how we can do this processing at the edge. And then reliability. So there's a lot of composite materials. So this is a real challenge too, where you're combining things like metals and plastic and carbon fiber. And that really ups this requirement for human inspection, which we're looking to solve. This metrological data can be captured from these shiny, transparent materials, particularly these composite materials. And the goal is to move to 100% inspection, particularly focused on the edge so we don't have to send it back to the cloud the whole time.
This inspection task demonstrates how automated edge AI can dramatically improve manufacturing processes, improve quality, save production time, reduce waste, reduce cost, reduce reputational damage, and increase customer satisfaction.
And now we're going to look at the use cases. So we have 2 primary use cases where this will be used. One is in high quality stationary scanning. So you take a 3D surface scan, you're able to calculate the color and reflectivity. We can run pattern matching for fixture gap analysis and external shape measurements. And we can inspect multiple types of materials in the same pass. And then really the second class of use cases fit into this idea of scanning moving parts and materials. So the idea of doing real-time analysis to reject or accept parts while they're on a production system. So literally as they're moving, it's able to find defects reliably and repeatedly, and you could set the tolerance for the size or number of defects perhaps in a given area. And we're going to look at some specific examples. So if we look at the automotive paint and glass inspection, for example, on a new car production line, you have these light bars, which essentially show up as reflections, as linear reflections in the surface of the car, and they enable visual inspectors standing around to pick up dents or scratches or maybe chips. There's any number of manufactured products that really make it a challenge to do this inspection. And so anything really metallic, you have this problem with it being, particularly as it's just been machined or extruded, very bright and shiny. So the reflectivity of things like aluminium extrusion or CNC milled steel parts. And certainly things like smartphone inspection. So a lot of consumer electronics really is a challenging area, and there's a lot of manual assembly because parts are difficult to see and therefore automate, or certainly manual inspection. And then we start to talk about the types of materials and the defect types. We can get into things like paint, glass, metal, and plastic, specifically looking for scratches and the depth of those scratches and the length of those scratches. For things like paint, coatings, metal, and carbon fiber, we can look for dents and gaps. And then for things like plastic and metal, you can look for the gaps and fit between those parts. For stamp metal, we can look at the contour dimensions. For stamp metal, we can look at burrs and edge shapes where there might be fully die cut elements. And for things like motherboard inspection, we look at parts and solder joints. But certainly there are many, many other examples, including powders, for example, in the pharmaceutical industry, textiles. There's a whole range of subjects where you have photometric properties that are excellent to collect using this process. Here's an example of some stamped metal parts. I think what's really interesting about this is you can see the pickled zinc on the galvanized coating of this part that's been put through a stamp and die. You can see the detail of the burrs formed at the edge where the punch and die meet, and the parts as they're being produced can literally be inspected with 100% inspection, and should these burrs reach the point where they exceed tolerance, you know it's time to perform um, some maintenance on the punch and die or swap the punch and die out for a new one. And this means you're not producing parts and going through taking them through your process, because this is probably combined with many other parts to make a final product. And this means you're intercepting those problems right at the point of manufacture. This is quite amazing. These are 10 millimeter, so 1 centimeter long scratches on glass, and you can actually see they almost form this organic shape like a rope as those chips come away from the lines made by the carbide scribe. But scratches and fractures, they will show up on glass, and they clearly manifest based on their type and structure of the way those are formed in the crystalline surface of the glass. So that ability to pick up these very, very difficult to see defects is really powerful. Here are some examples on a lacquer coating, so we can pick up things like ripples, inclusions, and pinholes. And in some cases, these are sub-millimeter in terms of size. So that ability to pick these up, even though the part is moving in a production line, is incredibly useful. And here's an example with a motherboard. So we're actually breaking this motherboard down into layers. We have what you'd see in a traditional image in the top left, so you can see shadows and reflections. In the top right, we just have the diffuse image, so that's just the color. So all of the shadows and reflections have been removed. In the bottom left, we can see the 3D shape. So it's the perfect place to see what components are there. You can see the details of the copper traces. You can even see the silk screen printing. And then on the right, bottom right, we can see the specularity or the shininess of the edges. So that allows us to see all of the solder joints. Particularly useful to know if there's any dry joints on the motherboard. And then within this context, we have the challenge that if you are using digital systems to perform inspection, how do you visualize those defects? So we're actually demonstrating this using augmented reality. And you can essentially bring in all of your manufacturing data via the NVIDIA Omniverse importers provided, and then we can visualize them on a MetaQuest headset. And that will allow us to see composed in the real world that additional data overlaying. And the great thing about this data is we have this technique called content density. So as I get closer, it's going to bring up more information. So let's go over to that paint scratch again. As I walk up closer to the vehicle, I can see the real scratch in the real world, and then above it, I can see the 3D scan, which brings up all the metrics and information about it. So it might give me information on how to fix it. And so something like this panel gap, no one's had to put a sticker there, no one's had to look at it manually and try and figure out what's gone wrong. All that automated inspection has happened, and now this has been delivered to the garage for repair, and I can see immediately where these issues are. So for example, this paint chip, it'll tell me information, so I know if I can just put some filler in with a cut and polish, and that might be acceptable to sort it out. And in conclusion, the ability to scan these very, very difficult materials, so reflective metals, glass and ceramics, plastics and carbon fiber, foil and film, polished surfaces, even mirrors. The ability to do this in real time, so very low latency, and to do it right at the edge using edge AI computation. And then the reliability, that ability to objectively, with automated AI inspection and 100% coverage, inspect your parts to isolate those layers of information and use those to make decisions right there on the edge as to whether the parts themselves are acceptable or whether the equipment that's manufacturing them is still within specification. Brilliant. Cheers.